Folks, I am so excited to be here for the 10th anniversary of GopherCon. I remember my first GopherCon in Denver, being just this young, terrified gopher, intimidated by the whole space. I remember the giant bear just pressing on the window, the blue one in the Mile High Ballroom. So indeed, I'm Filippo. I'm one of the maintainers of the cryptography standard library, and I've done that over the years with many other people, including Katie Hockman, Roland Shoemaker, Damian Neal, and Nicola Murino, and so many others from the community. I was previously at Google, now independent, and we're going to talk a little bit about that at the very end. But first, let's talk cryptography. So today I'm here to tell you about all of the stuff that happened in the past year that excites me in the cryptography libraries, and about some of the plans we have for the future. The cryptography standard libraries are all of those packages that come bundled with the Go toolchain that you use to make secure connections, TLS, hashing, encrypting, and so on. And let me tell you, it's been an exciting year in the world of cryptography and in the world of Go cryptography. So let's get started because we've got a lot of ground to cover. The main thing that has had all of us busy is post-quantum cryptography. So post-quantum cryptography is about the future. We are worried about this new kind of computers that scientists are working on called quantum computers. They don't exist yet, to be clear. But they might exist in 30 years or 50 years or 20 years or never, depending who you ask. But we're a little uncomfortable with that because with those computers, you'll be able to break any asymmetric cryptography we're using today. So your symmetric stuff, your encryption, your hashes, those are fine. But stuff like signatures and key exchanges, those would be broken. And signatures is not too much of a problem. It's not like somebody can build a quantum computer in the future and then use it to go back in time and use a fake signature today to hack your systems. However, key exchange is a bigger problem. If you make a connection today and somebody records it, whether it's SSH or TLS connection, and then in 30 years they develop a quantum computer, they can crack the recording of the connection and extract secrets you might have stored in there, which maybe you trusted to stay secret much longer than 30 years. So that's our problem. The good news is that there are algorithms that are hard for quantum computers to crack. And those algorithms can run on regular computers. So post-quantum cryptography is not what we do on the quantum computers. It's what we do today on these computers that is safe from the quantum computers of the future, which is good because I have no idea how quantum computers work, honestly. Now, there's a misconception that post-quantum cryptography is slow. It's actually very fast. It's even faster than the classical cryptography we use today. The problem is that it's very large. So while a key exchange today takes about 32 bytes in the handshake, a post-quantum key exchange can take a kilobyte to send over the wire and back. So a lot of the engineering has focused on how to work around that and making sure the systems work for that. The other thing to know about post-quantum cryptography is that it's new. This means two things. One is that we're not as sure about its security as we were about the classical stuff that we've been using for the past 30 years. So how are we going to handle that? We're going to use hybrids. Hybrids are algorithms that do both post-quantum and classical at the same time, then hash them together, and the final result will be as secure as both of them. So even if the new stuff turns out to be broken, it's just as good as the old stuff. And if instead quantum computers come in 30 years, then there will be the post-quantum part that protects us. The other thing, the other consequence of how new they are is that they are still drafts. So the main algorithm that we're implementing used to be called Kyber, and is being standardized by the US government, by NIST, with the name MLChem, because we can't have nice things, and so all the names have to be boring. So that's what we're implementing today. In practice, there's a new package in Go 123, which is internal for now, called MLChem 768. That's how you use it. And it's aggressively optimized for readability and for understandability and for safety. It's just 500 lines of code, plus 300 lines of comments and many, many more lines of tests. And it was written from scratch from the specification. we did not port it from the reference implementation, and that turned out to be a pretty good choice because the reference implementation, 2 vulnerabilities were found in the last few months in it, and we were safe from it because we started from scratch from the original specification. It's also been extensively tested. We have exhaustive tests for all possible inputs of some of the lower level stuff. We have 95% test coverage. We have test coverage for things that have a chance of happening of 1 in 2 to the 38 times. That's billions and billions. And we shared all of those tests on CCTV for other implementations to use. It's a public test suite. And other implementations that used this actually found bugs in their implementation thanks to the test vectors we've shared. So I'm very proud of that. So we focused on safety, but we actually ended up with something that's actually fairly fast, and I'm very happy about that. We got that by doing the usual stuff you do for high-performance Go cryptography. So we minimized heap allocations, we did bounce check elimination, and we designed the API to help us reuse pre-computed values across different steps of the key exchange. The final result is that MLChem 768 key exchange is, depending on whether you start it or you receive it, is a little faster or a little slower than X25519 key exchange. So we're squarely in the ballpark of the classical implementations. With a difference, though. There is no assembly in this implementation, while there's plenty of assembly in the X25519. Thank you. I'm so happy about that. Whoever's clapping knows how much I hate assembly. I've been on this stage so many times to tell you that. All right, so how do you get the good stuff? Go 123 comes out in a month, and it will only have the new draft hybrid in CryptoTLS by default, but there's no way to configure it and no way to use it from the API because it's still a draft. We have the backwards compatibility promise, and we don't want to promise to support something that's not final forever. But if you don't touch anything, CryptoTLS will automatically use post-quantum already next month when you connect to Google, when you connect to any other Go service, and I'm very happy that we're getting ahead with that. But hopefully, NIST will publish the final standards in, they said summer. I think it's summer. We're all waiting for them to drop. And after those are out, hopefully in Go 124, we'll expose the package so you can use it directly, and we'll expose configuration options so you can tell TLS to always use that. And hopefully in the future, we'll also bring the MLChem implementation to Xcrypto SSH when SSH standardizes a way to use that algorithm, because they're using something slightly different for now. So if you're curious, that's a QR code that will take you to a longer blog post about the implementation work on this, and also to a blog post that explains all of the math you need to understand to read this original MLChem specification, which is actually very readable. So I encourage you to do that. You don't need to understand lattices, none of that. Just some of the matrix.product stuff, which is explained in the post. Now, speaking of CryptoTLS, another change that I'm very happy about in Go 123 is that we tweaked the defaults a bit. This is how you used to have to configure CryptoTLS to make sure you are using only modern versions and modern cipher suites. This is how you have to configure it in Go 123. All of the things are gated behind both Go debug flags, if you need to turn them on and off for debugging, and behind the Go version in your Go mod. So if your Go mod says Go 122, will behave like we did in Go 122. If it says Go 123 or higher, the defaults will change. If you still need to use the old stuff, it's still there. You can still enable it with your config. What we've changed is the defaults, so that if you don't really want to think about ciphers and versions and TLS because you've got better stuff to do, that's what you can count on us for doing. We'll just keep bringing the defaults forward with new releases of the language. Another thing that's coming that I'm very excited about in CryptoTLS is encrypted client hello. This is a new specification which works on the client hello, which is the first message that a client sends when it opens a TLS connection. And that message is not encrypted. Most of the connection in TLS is encrypted, but this is too early to have keys. So it sends the name of the website you're connecting to and the protocol you want to use in clear text. And you might say, who cares about that? The IP address is public anyway, right? Well, maybe you're connecting to a CDN that has many different websites, so you might want to hide which website you're connecting to. And that's what encrypted client hello does. It does that by taking the real client hello, encrypting it with a key that it got from DNS, and then sticking it inside a outer client hello with a fake name on it, and then deciding a lot of rules for how to handle when the server goes like, what's that? And it's actually a little complicated. I'm not the biggest fan of how it came out, but it's an important piece of specification we had to implement. And Roland did an amazing job implementing this, so I'm actually happy with how we landed it in Go 123. And looking even further into the future, we're considering implementing transparent support for kernel TLS, maybe in Go 124. Kernel TLS is when you do the handshake in Go, just like now, but then you go to the kernel and you say, hey, here are the keys to do the connection. And you do the encryption, and you do the decryption, and I'll just give you plain text bytes on the socket. And if you're doing normal amounts of traffic, this is not super interesting. But the reason it's useful is if you're doing a lot of traffic, it really improves latency and throughput, because now the kernel can just, for example, proxy from one connection to the other without even passing through user space. The reason we haven't done this yet is that it took a bit for Linux to implement support for TLS 1.3 and all directions, but it looks like in 2022 it's stabilized enough that we'll just do it transparently for you if we think that the kernel supports it. Great. So now let's talk about randomness. Let's imagine that you're making a website and you just want the background to change color every time it's loaded. This is not a security relevant thing, so you just use mathran because it lets you do int n and get your random color every time. But then later you implement logins, and now you need to implement password reset. So in the same file somewhere else, you write a function that generates a password reset token. And you go like, I know how to get some random bytes. I'll just do rand.read. And that will just fill some randomness into my buffer, and then I'll just encode that. Well, the problem with that is that you're just using mathrand to generate things that are now relevant to security. And that happened in the production to some folks. And as of Go 122, there was no secure way to use mathrand. You can't seed mathrand in a way that that's secure. If you use mathrand for something like password reset tokens, I used to be able to just, for example, ask to reset my password 100 times, and then be able to predict the next token. And then I would ask to reset Angelica's password, and I wouldn't get the email, but I would predict the token, and so I could reset her password. That's bad, and that happened in production. Now, we could have just said, well, bad Go developer, don't use mathrand for security-relevant things. It's your fault, really, not mine. But that's not really the business we're in. We're in the business of making your application secure, not in the business of not taking blame for how your applications are not secure. So we really wanted to put cryptographic randomness in mathrand, but the problem is that usually the complaint was, oh, but it's too slow. Well, that sounds like a challenge. So we went and got Cha-Cha-20, which is a common stream cipher. We took the reduced round version of it, which there is a pretty good paper called Too Much Crypto by J.P. Omason that makes the argument that it's still secure because the margin of security is very wide. We made some changes to it to make it easier to use for SIMD and faster to parallelize and vectorize. And then we wrote a specification for it, which you can find at C2SP. And the final result is that it's just barely slower than the non-secure random number generator we used to have in mathrand. So with that, we just went everywhere and in Go 122 replaced the default generator of mathrand at the package level, the default generator of the runtime, and the generator of mathrand v2, which is the new version of the mathrand package. And they all use Cha-Cha 8 rand now, which will be is seeded from system entropy. So if you make that mistake, you're safe. We wrote more about that and about how we had to work within the bounds of the backwards compatibility promise to upgrade the security of Go programs without breaking any of them. So you just update your program, and now if you were making mistakes that were affecting security before, now they're probably not affecting security anymore. Still, don't go back and say, oh, Filippo said I can use mathrand for cryptography now. I didn't say that. You still should use cryptorand. But if you use mathrand in a belts and suspenders kind of way, you will be safe now. Now, that means, though, that you need to use cryptorand, which returns an error if from read. And so now your password reset token looks like a function looks like this, and you're a little worried about panicking, like, does it fail? What do I do? Filippo, you made my code look worse. It looked so much better when I used mathrand, damn it. Yeah, all right, fair enough, fair enough. So what if cryptorand read fails? Wait, does cryptorand read ever fail? So we went in there and we looked at all of the major platforms, and on Windows, the thing we use says always returns true. Great. On macOS, we migrated to a new API which says these functions are always successful. Great. And on Linux, the documentation says a return of your bytes and request should never happen, but the careful programmer will check for this anyway. Which is not as reassuring, I gotta say. But we went in there, looked at the kernel source, and it's gonna be fine. We can always get randomness from the system as long as the get random syscall is available. And that syscall was added in 3.17, which came out in 2014. So that's going to be the new minimum supported version of the kernel. Ha, solved. So that means that we can guarantee that it never returns an error. And I'm not talking about it will panic if something goes wrong. If something were to go wrong for some reason that I can't even imagine because we went through it and we are certain that all of them don't return errors, we will just crash the program. So that you can't be like, oh, but I want to be extra safe, so I want to implement a fallback that uses the timestamp if we can't get randomness from the system. No, I'm going to crash your program. You don't get to choose. But the point is that that will never happen because we went in there and changed the APIs we use to the ones that are safe. And the final thing that lets us do is that it lets us add new APIs that don't return errors at all and are much more ergonomic. So for example, we're talking about adding a text function that just returns a string of random characters that you can use for stuff like tokens and passwords if you need to. And that means that your function now looks extremely short. And if you have opinions on this is still an open proposal. So you should join the conversation and tell us if it does what you need it to do. So this was just the highlights. There is so much more that happened in the past year in the cryptography libraries. Work done by many folks like Roland, who work on X509, on being a little stricter with what certificates we accept, and Damien, who implemented new zero-RTT APIs for Quick, and some new contributors who are working on better testing for crypto-TLS, for crypto interfaces, and even porting the old assembly, handwritten assembly, to the AVO generator. I'm very excited about all of these. But one thing that I want to highlight is that we finally recovered all of the performance loss of crypto RSA that had regressed when we moved to a new, safer and constant time backend. What happened is that I thought I had made it just like 20, 30% slower. And then you folks kept complaining to me about it. And I was very confused because I was like, why do you care about 20% slowdown in verification? It was 5 times slower. I had not realized my benchmarks were broken. My bad, sorry. But then it got personal. And so I went in there, and it's now faster than when it used the old insecure variable time backend. So goddamn it, we put that to bed. And, you know, sorry about the slowdown for a couple releases. That was my bad. Now, stepping outside of the standard library for a second, I want to talk about the Xcrypto SSH package. Because the previous maintainer stepped down a few years ago, and it had gone basically unmaintained for years. Last year, we got Nicola Murino to start working on it, and he's been doing amazing work. He's merged more CLs in the last year than were merged in the previous 3. And he's implemented stuff like multi-step authentication, much better support for SHA-256, which was, let me tell you, a mess to implement because it used to be very coupled which key type and which hash you are using. And then SSH had to find a way to specify the hash separately. And that caused so many bugs in all of the implementations. So there's a lot of work to be still compatible with all of those bugs. And Nicola has been doing amazing work on that. And the result is that now you can configure Xcrypto SSH to not use SHA-1 for anything, anywhere. And I'm so happy about that. The other thing that I'm very proud of is that we were 5 years behind on this one. But now that Nicola is there to do maintenance, we implemented one of those features, the ping protocol, before OpenSSH even released it. It was still on the main branch of OpenSSH when we released it in xcrypto.ssh. We went from lagging behind by years to being ahead by a few weeks. And I'm so happy about that, and that is all Nicola's work. Great. So we talked a bit about the things that we've done in the past year or two. Now I want to tell you about the plans for the future. What are we planning to do for the next year or two, or even looking further in perspective? So you've heard me talk about the standard library and xcrypto, and there are a lot of misconceptions around that. Some folks, who here thinks that xcrypto is the experimental packages? Raise your hands. I think I spoiled the answer there. And some folks think that they're the insecure ones. And honestly, those are understandable misunderstanding. There is a lot of old stuff in there. And if we went back and, we deprecated a bunch of it a few years ago, and that was a lot of fun. I wanted to get a deprecation hammer done, but they wouldn't let me keep it in the office. So I found out you can just get signs printed. That's fun. But after the deprecations, the number of packages was a little more manageable. And we're doing another round of deprecations and freezing, which leaves behind a fairly well-scoped set of packages, which we're now planning to move to the standard library, so that xcrypto will be no more, and there will be no confusion about the level of support and backwards compatibility of those packages. Very excited about that. Next, we're going to work on some new APIs. One that I'm very interested in is the new AEAD API. Because in the past, if you wanted to encrypt a message in Go, you would have to use either ASGCM or ChaCha20 Poly 1305, which return a type that implements the AEAD interface. The AEAD interface asks you to deal with the nonce, with the initialization vector. And that's something that confuses a lot of developers, because to be fair, it's a little wonky what exactly you're supposed to do. And it changes depending on the nonce size. Some nonces are too small to generate them randomly. It was a bit of a mess, and we didn't want to delegate all of that to you. But to take on ourselves the management of the nonces, we needed them to be big enough to be safe to generate randomly. And a lot of AADs don't let you do that. So we went back to the drawing board, and we're working on some higher level wrappers around common AADs, which we'll be able to use to implement a higher level API, which just takes a key and a message and encrypts it, or takes an encryption and a key and decrypts it. And you don't have to think about nonces ever again. And I'm very happy to bring those to one of the future releases. Speaking of APIs coming to the future releases, there's an approved proposal that needs implementing for the runtime secret package. So the problem here is handling what other languages handle with just safe zeroing. What if you really need, you're dealing with some really sensitive keys and you want to delete them from memory after you're done with them? For example, because your server has an uptime of 100 days and you don't want somebody who hacks the server in a month to be able to decrypt yesterday's connections. That's fair. But this is something that I always thought was not possible to do securely. If you go to that proposal and scroll to the top, you'll find me saying we're actually not going to do that, because everybody who offers those ways to do that in the language then offers ways that are too brittle, and in the end, it's too hard to do it securely. So we would just blame the application for what is really giving them a bad tool. I was wrong. We over the years in that proposal, we came to an idea for an API that I'm very happy about, which is this secret.do function, which takes a closure, and anything you do in there is considered extra sensitive. So when that function returns, the entire stack of the Go routine will get zeroed out. If the stack of the Go routine grows, the old one will get zeroed out because the runtime is in on it. There is collaboration from the runtime. And finally, any heap allocation that happens during that span, like that key allocation right there, is flagged so that when the garbage collector comes along, it will automatically zero it out and remove it from memory as it's being garbage collected. I am very happy about that API style. And the fact that we didn't know how to do it years ago is a great example of why I really like this quote. No is temporary, yes is forever. If we had implemented what we knew how to do years ago, it would have been way less safe than what we now know how to do. So if sometimes we see us being reticent to implement something that you really care about, know that part of the time is because we want to wait until we know exactly how to do that right for the next 15 years of the standard library. We are actually going to use that API for another thing. So we write constant time code for cryptography. And how it works is that we write this code that will never change its timing based on data. And then we give that to the CPU. And apparently the CPUs now will go like, you know what? I'm going to read the data and make decisions based on it. So I'm going to take your constant time code and run it in variable time because it's faster. Anyway, then the researchers come along and are like, oh, we can use that to extract keys from the Go standard library. Well, no shit. We wrote constant time code and then the CPU made it variable time. Anyway, they now add the mode that we have to enter to have our constant time be actually constant time. They call it dot or dit or do it, whatever. We're going to have a similar API, just like secret.do, which is going to be constant time.do, and will run those spans in actually constant time. And Roland is working on that and benchmarking that, and it's extremely painful, but hopefully after that we'll have an understanding with the CPU architects that. Can you tell me I'm a little miffed? Yeah. Anyway, moving on. Another thing we're planning to do is get proper support for FIPS 140 in the upstream toolkit. If you've never heard about FIPS 140, great. Keep doing what you're doing. You're doing it right. Don't look back. Just. If you care about FIPS 140, now is the time to talk to us because we're finalizing plans for how to do it and what architectures to plan to test it on, and we're planning for it to be a much smoother experience than the current boring crypto one. Okay, so we spent some time looking forward to our future plans, but I want to take a couple minutes to just look back at the track record of the Go cryptography libraries because it's now been 10 years since they've been first published. And so I went back and retriaged all the vulnerabilities that ever affected the crypto packages in the standard library. And assessing the severity of something in the standard library is really hard because the impact depends on how you use it. Something that could be a low level, a low severity vulnerability in one application, but a high severity vulnerability in another application. So instead, we're going to use a much more scientific scale, which is how unhappy and stressed they make me. And this is the result of that. I want you to just get an overview. No need to read the specifics, but I want you to notice something. That black line over there is the 5 years ago mark. So in the last 5 years, we've had only 4 medium stressing Filippo out vulnerabilities. And 2 of them were things that affected everybody in the ecosystem, the Terrapin attack and the Marvin attack. And the other 2 were in kind of edge settings. All of the other ones are just denial of services or things that we just fixed just to be safe. If you look at the 5 years previous that, there are more yellows and then 4 really scary ones that led to key recovery attacks and scary stuff like that. To be clear, none of those are remote code execution, so we're already ahead of most other cryptography libraries on that. But the thing I'm really happy about this is that you can see a pattern of moving towards lower and lower impact in the vulnerabilities over the years. And I'm very happy about that because it means that the effort we put in to improve the testing and do the rewrites of the scariest part of the code base are paying off because now the things we're finding are there's less and less low-hanging fruit and the scary stuff is much more shored up. If you want to play with that, there's the spreadsheet is public and I plan to keep it up to date. So one last thing I want to mention how I get to do this work. I left Google in 2022 to look for a sustainable way to do open source maintenance at large. And I've been doing all of this work thanks to the retainers paid to me by my clients. And just 3 days ago, I've announced the next step in that process, in that journey, which is expanding that to more maintainers and more projects. I'm calling that organization of open source maintainers GEOMIS. And at the start, it's me, Nicola Morino, who does Xcrypto SSH, and I'm happy to announce Dominic Honev, who maintains Static Check and GoTrace UI. So now all of the work you're hearing about and the work of Nicola and the work of Dominic are made possible by the retainers of my clients. These are the first clients of GEOMIS who get to have safer who get to de-risk their dependency and know that all of these things will be maintained properly, and who get direct access to our expertise when they need it and when they don't have it in-house. So I encourage you to read the announcement if you want to know more. We're also sponsoring GopherCon, so we have a table right across that wall. And please email me if you have any questions. And thank you very much.